Okay, so in this video, we're going to continue talking about different types of circuits. And there's different ways to connect resistors together in circuits. And the two primary ways are what's called in series and in parallel. Now, I always say definitions are important, so please make sure you understand the definitions that separate these two. But by definition, components that are connected in series have the same current flowing through them. Okay, and so that basically means that if you look at the space between two components, if there's no junction between two components, then those components are in series. Um, Components in parallel, and I say components rather than resistors because they don't have to be resistors. There's lots of different circuit components that we're not going to talk about. So I just say components to be more general. But components connected in parallel have the same voltage across them. Okay, they have the same potential difference across them. And we've seen some basic examples of each of those before in the last video. Okay, now you can also have a combination circuit where you have resistors, some of which are in series and some of which are in parallel. Okay, and before we get to doing actual examples, what we're going to do is we're going to talk about the concept of what's called equivalent resistance. Okay, so pause it here if you need to add this to your notes. So basically the idea of equivalent resistance, or what's sometimes called total resistance, is it gives you a way to simplify a circuit down. And so you can have a complicated circuit. Let me open up my Epic pen. You can have a complicated circuit, and basically the goal is to reduce the circuit down that might have, 3 or 4 or 5 or 10 or 20 components into it. And basically you want to reduce it down to one single resistor with one what's called equivalent resistance, okay, or sometimes called total resistance. Okay, so it's the idea of reducing a complicated circuit down to a simple circuit. Now there's two equations that allow you to add resistors together to find the equivalent resistance. Okay, and that depends on whether or not the resistors you're adding are in series or in parallel. Now these two equations, by the way, are both given in the in the data booklet, but they're not labeled. Okay, so make sure you add this to your notes. In order to add resistors in series, what you do is you just add the resistances. And that's it. Okay, and so R1 plus R2 plus R3 plus dot dot dot, that just means you add up however many resistances you have in series, you just add those up. Okay, whether it's, 1 or 2, 3, 100, doesn't matter, you just add them up. Now, to add resistors in parallel, the equation looks slightly different, and it looks like this. It's 1 over Req, and again, Req is just the combination of two or more resistors. Okay, 1 over Req is 1 over R1 plus 1 over R2 plus 1 over R3, etc. Okay, and so make sure you understand how to add resistors in series and how to add them in parallel. Now, practically speaking, a lot of circuits are a combination of these two. Okay, and so sometimes you'll have to add some of them in series and then others in parallel. Always make sure that you understand the difference in the definition between series and parallel circuits. Just to review, components in series have the same current going through them, and components in parallel have the same potential difference. Okay, now, once we have taken our complicated circuit and reduced it down to this, then we can just use V equals IR. And as long as we know what the V is, and we know what Req is, then we can find what's called the total current, I total. And the total current is just how much current is coming out of the cell or out of the battery. And that current might split at multiple junctions throughout the circuit. That total amount is what comes directly out of the cell. Okay, so pause there, make sure you have those equations in your notes. Okay, so when we're simplifying circuits, just a few suggestions. Usually you want to try to work your way from the outside in. You want to start at the outside of the circuit and work your way in. Simplify different pieces of the circuit using the definition of series and parallel components, and keep on going until you can simplify it down to a single overall equivalent resistance for the entire circuit. Once you have that, then you can use that REQ value to find the total current flowing, and then you can use the loop rule and the junction rule to solve for the rest of the circuit. Okay, and so that's basically the approach we're going to be using to solve circuit problems. Okay, now, just to give you one more hint, as far as, how do you recognize parallel components? What happens a lot of the time is people will see a parallel circuit and then they'll get it into their mind that a parallel circuit has to look a certain way. Okay, but remember there's a specific definition for being in parallel, and that means that the components all have the same potential difference. Okay, so add this to your notes here. But basically, here is a trick for very quickly being able to recognize if components are parallel with each other. And it all goes back to Kirchhoff's second law, the loop rule. Okay, the loop rule that says the sum of the voltages along a closed loop have to add to be 0. Now, because of the loop rule, if you can make a closed loop that only has 2 voltages in it, if those 2 voltages add to be 0, that means those 2 voltages have to be the same number, just with opposite signs. In other words, if you can make a closed loop that only has 2 and exactly 2 components in it, those 2 components must have the same voltage and therefore must be in parallel with each other, okay? Because that's the definition of being in parallel. And so that gives you a really quick way of assessing whether or not resistors are parallel or not. If you can just, look at the circuit and in your mind make a closed loop that only has 2 things in it, those 2 things must be parallel. Okay, so make sure you add that to your notes, and we're going to do some examples of equivalent resistance. Okay, so example 1, we're asked which resistors are connected in series and in parallel, and then we're asked to calculate the equivalent resistance of the circuit. Okay, so here we have a circuit that has 4 different components in it. Okay, so let's see if we can figure out which of these are in series and which of these are in parallel. All right, so what's going to happen is current is going to come out of the cell, and it's going to go through resistor R1 right here. Okay, so I'm going to call that current I1. Then that current is going to hit this junction, and it's going to split into currents I2 and I3. I3 is going to come down here. It's going to recombine with I2 at this junction, and that means that the current going through R4 is also I1 because that is how much came out of the cell to begin with. All right, so keeping that in mind, using the definition of series and parallel, I can immediately tell that R2 and R3 are parallel with each other. Okay, and the reason I know that is, let me erase this. The reason I know that is because I can make a loop, boop, that has 2 components and only 2 components in it. Anytime you can do that, those 2 things are in parallel. So when you're simplifying a circuit, you usually want to start with the outside and work your way in. So the first thing I'm going to do for the circuit is I'm going to add R2 and R3 in parallel. In other words, I'm going to reduce the circuit down to, here's R1, here's R2 and R3, and here's R4. Okay, so my first step is basically to combine R2 and R3 and simplify it down to this. Now, to add R2 plus R3, I need to add them in parallel. So I need to do 1 over REQ equals 1 over 30 plus 1 over 50. All right, and so I'm going to do that in my calculator. I can look at that and recognize that I can use a common denominator of, let's say, 150. Okay, so that would be 5 over 30 plus 3 o over 150, sorry, 5 over 150. Okay, and so 1 over REQ would be equal to 8 over 150. And so REQ would be, if I flip this, okay, I do 150 divided by 8, I get 18.75 ohms. So in other words, I can simplify my original circuit down to this, where this is 18.75 ohms. R1 is 20 ohms, that's a given. And then R4 is 20 ohms, that's also given. Okay, now once I have it simplified down to this circuit, I can go one further step, look at this and recognize all three of these resistors are in series. And I know that because they all have the same current through them, because there's no junctions anymore, because I reduced the circuit down from this to this. Okay, so now I have three resistors in series. I can take it one step further and simplify down to this, where this is my total REQ. This is 10 volts. And here REQ, if I just add these three in series, I get 20 plus 18.75 plus 20 equals, let's see, 58.75 ohms. Okay, so in other words, the overall equivalent resistance of the circuit is 58.75 ohms. I've simplified it down, and this circuit is mathematically equivalent to this more complicated one, which means now if I want to, I can use V equals IR. I can do 10 equals I times 58.75. And this I is going to be I total, how much current is um, coming out of the cell. So 10 divided by 58.75 is 0.17 amps. And then if I wanted to, I could go on to further analyze the circuit using the loop rule and the junction rule. Okay, so basically 0.17 amps comes out here. It's going to split here, and I know it's going to split proportionally, and I can find I2 and I3 by using the loop rule. Um, and then the current recombines here, and that 0.17 amperes runs through R4 and back into the cell. And I'm not going to do that because I want to do one more example, but that's basically how you would use equivalent resistance, is to take a complicated circuit and simplify it down to a less complicated circuit. Okay, so pause it there and look some more at example 1. Okay, so example 2, this is actually an IB question. Okay, this is a multiple choice question from an IB exam a couple years ago. So see if you can answer this question. It says 4 resistors are connected as shown. Notice that they use the rectangle symbol for resistors as opposed to the squiggly line. Now you can talk about equivalent resistance or total resistance without talking about like the voltage of the cell. Okay, so all we have here is resistors. We basically only have like the resistors themselves, and we don't have like a voltage source. Okay, that's fine. So we're asked, what is the total resistance between X and Y? Okay, so see if you can figure out the answer to this question. Okay, so the first thing I would look at is, do I have any resistors in series or parallel? The 2 ohm and the 8 ohm are not in series because any current that goes through the 2 ohm resistor, that current is not going to go through the 8 ohm resistor because it's going to split right here at this junction. Okay, likewise, the 2 ohm and the 6 ohm, those are not in parallel because I can't make a closed loop that only has those two things in it. Okay, but what I can do is I can start with my two 8 ohm resistors. I can make a closed loop that only has those two components, meaning that by definition, they have the same voltage and therefore are in parallel. And so first I'm going to simplify the circuit down by adding the two 8 ohm resistors in parallel. So 1 over Req equals 1 over 8 plus 1 over 8. That's 2 over 8. which means that the combination of those two resistors is 8 divided by 2, which is 4 ohms. And so basically, I've simplified this down, so ignore that. And basically what I now have is a circuit that has these two resistors and then this resistor down here. Okay, so ignore this upper path. I've basically just simplified it down to 1, 2, 3. Now that I've made that simplification, the 2 ohm and the 4 ohm resistor are now in series because I've simplified these two down, so there's basically no more junction here. All right, because basically what I have, just to draw this another way, this is basically what I simplified down to. This is Y, and then this is X. Okay, so that's 2 ohms, that's 4 ohms, that's 6 ohms. Okay, now the 2 ohm and the 4 ohm are in series, and so I can find the equivalent resistance between those two just by doing 2 plus 4, which is 6 ohms. In other words, I've now reduced this circuit down even further, and now I've reduced it down to, oops, did not mean to do that. I've reduced it down to this. Okay, so I end up with 6 ohms and 6 ohms in parallel. And so the answer to the overall question, because once I simplify those two, I'm basically done simplifying, is 1 over 6 plus 1 over 6. Okay, so 1 over Req is going to be 2 over 6. So the overall Req is going to be 6 divided by 2, which is 3 ohms. And so the answer is A. Okay, so pause there if you need to look at that some more. Okay, so you do have practice worksheets to work on regarding equivalent resistance. I would highly encourage you to work on those. Um, but I do want to move on and talk about one more thing um, before we finish up this video. So let's see. Can do that one in class. Okay, the last thing I want to talk about in this video is measuring devices. Okay, and so there's two important measuring devices that you need to be aware of, and that is called an ammeter and a voltmeter. Okay, so pause here, make sure you add this to your notes. Okay, so basically the purpose of an ammeter is it's used to measure the current flowing in part of a circuit. Okay, an ammeter reads whatever current flows through it. Now, typically, ammeters have a very, very low resistance so as to not affect the current that you're trying to measure. And I'll talk more about that in just a second. Ammeters have to be placed in series in the location where you want to find the current, and an ideal ammeter has zero resistance. The way this looks in a circuit diagram is you draw a circle with a capital A for ammeter. Okay. An ideal ammeter would have zero resistance. And the reason for that is because of what's called the observer effect. And so you don't want to make a measurement where making the measurement will affect what you're trying to measure. Okay. And so for example, if the ammeter has a high resistance, just putting that measuring device into the circuit is going to change the circuit itself. Okay. And there's no point in measuring something that's not going to be accurate because the measuring device itself is messing up the measurement. Okay, so in an ideal situation, an ammeter has zero resistance. Of course, in real life, typically they do have some finite resistance, but ideally you would want that to be zero. Now, a voltmeter is used to measure the voltage between 2 points. It reads whatever potential difference is across it, meaning that you always want a voltmeter to be parallel with whatever you're trying to measure. Because if it's parallel to what you're trying to measure the voltage on, then whatever is on the voltmeter is going to be what you're trying to measure. Okay, a voltmeter typically has a very high resistance so as to not draw any current towards it. Because again, if some current like split off and went through the voltmeter instead of the circuit, that would affect what it is you're trying to measure. Okay, so an ideal voltmeter would have an infinitely high resistance. Okay, so make sure you have that in your notes. Okay, so we already talked about the observer effect. Um, when we measure voltage or current, we want to minimize the effect that our tool has on the circuit. Here you see the symbols for voltmeter and ammeter. These are both analog versions of a voltmeter and ammeter. We have these in the classroom for your use. You can also buy what's called a digital multimeter at the store. You can buy this at any hardware store, Home Depot, Target, Walmart. A lot of people have these just like around their houses if they want to check the voltage on something or they want to test the current through something to see um, if a circuit in their house is working, especially if you do like a lot of work, like mechanical work, like working on your car or stuff like that, you might have a digital multimeter. And these range anywhere from $15 to $50, depending on the quality. Okay. Okay, so if you want to test something in your car to see if there was like a short circuit or to see if like, something burned out or, whatever, you would use a digital multimeter. Okay, so we talked about this before, but an ammeter is hooked up in series with whatever it is you want to measure the current through. And so if I want to measure the current through this component right here, I need to put an ammeter in series with that component. Okay, and an ideal ammeter has 0 ohm resistance, even though a lot of the time in real life it does have some finite resistance. Okay, that's just the ideal situation. Now, what happens if the ammeter is not ideal? So, for example, here we have a question, what is the reading for the current flowing through the ammeter if it has an added resistance of 1 ohm? Okay, so let's say this ammeter is 1 ohm, okay, and I want to find the current flowing in the circuit. Well, basically now I have 3 components all in series, and so I would want to simplify that down. Okay, so REQ would just be 5 plus 5 plus 1. Okay, that would be 11 ohms. And so that lets me simplify the circuit down to where this is 10 volts, this is 11 ohms, and then I can use V equals IR to find the total current. Okay, so I total would be 10 divided by 11, and 10 divided by 11 is 0.91 amperes. Okay, so that's how much current would flow through the ammeter if it had a resistance of 1 ohm. Now, what if we took the ammeter out? Okay, so what if the ammeter was gone? Well, the process would basically look the exact same, except when I want to find the equivalent resistance, I wouldn't have this one right here. Okay, meaning that the equivalent resistance would be 10 ohms, meaning that the new total current would be 10 divided by 10, which is 1 ampere. In other words, we have a circuit out there, the current going through it is 1 ampere. Okay, just by me sticking my measuring device in there, I measure a current of 0.91. In other words, my measuring device has changed the reading that I would have gotten without the measuring device, which is not good. Um, and so this is not really a good ammeter to be using for this situation. Remember, an ideal ammeter has 0 ohms, so that way when you add it into series, it doesn't change what it is you're trying to measure. All right, so let's see. Moving on. Okay, we talked about that. Um, a voltmeter, you always hook up in parallel with what it is you're trying to measure the voltage across. And again, an ideal voltmeter has infinite amount of resistance because you don't want any current going through the voltmeter because again, that would change what it is you're trying to measure. So for example, the current comes out of the cell, okay? It hits this junction right here and it's going to split proportionally. Now, you don't want any current going through the voltmeter because then it's going to change what it is you're trying to read. So if the voltmeter had an infinite amount of resistance, then when the current hits this junction, none of it's going to go through the voltmeter. All of it's going to go through the component, which is what you want to happen. Okay, and so you want, ideally, you can't have infinite resistance, of course, but ideally you want the resistance on the voltmeter to be very, very, very high, much, much higher than the resistance of the component, so that when it splits proportionally, a very small percentage of the current goes through the voltmeter. Okay, so let's say what happens if you have a situation where the voltmeter is not ideal, because an ideal voltmeter has an infinite resistance. So let's say we have this situation here. Okay, so we have a circuit set up. We have a 12-volt cell, we have two resistors, and we have a voltmeter. And it says the reading on the voltmeter is 7 volts. Okay, and let's say I want to find the voltage and current through everything. Okay, so um, first of all, if the voltmeter reads 7 volts, that means the voltage across R1 is also 7 volts. Okay, so that means this is 7 volts, this is 7 volts. Okay, because if these two are parallel, they have to have the same voltage. Okay, now I have 12 volts down here. So if you just think in terms of the loop rule, if I go up 12 and I go down this many volts, and then I go down 7 volts here, I have to get back down to 0, which means the voltage here across R2 has to be 12 minus 7, which is 5. Okay, so R2 has a voltage of 7 volts. The total voltage is 12. And now, if I want to, I could go on and further simplify the circuit. I'm not going to, just to save on time. But just that voltmeter being there has kind of affected what I want to do with measuring the voltage in the circuit. All right, so take a look at example 1. This is a multiple choice question. Okay, so the first part of the question says, which of the following circuits shows an ammeter and a voltmeter correctly placed in a circuit? Okay, so see if you can answer that. All right, so the answer to this question is 4. Okay, so each of these circuits, besides 4, has severe issues with it. Okay, so we're assuming that this is an ideal ammeter and an ideal voltmeter. All right, so here's my issues. All right, if you look at, let's start with the first one. If you look at the first one, current is going to come out here, and it's going to hit this junction, and it sees 3 options. Either it can go through a path that has some resistance, or it can go through a path that has no resistance, because remember, an ideal ammeter has 0 resistance, or it can go through a path that has infinite resistance. All right, now normally it would split proportionally, but what's actually going to happen is it's going to say, aha, this path has 0 resistance. I'm going to go this way. So none of the current is going to go through V, none of the current is going to go through R. It's all going to go through the ammeter. And this is a very bad and dangerous situation. This is called a short circuit. Okay, because basically what happens is you have a lot of voltage that normally would get used up in the resistor but can't. And so here that voltage has to get used up inside the cell or inside the battery itself. Okay, this is very dangerous because if that power is dissipated inside a battery, it can cause the battery to heat up and possibly explode, which is really bad. Okay, so you never want this situation. The issue with R2 is that basically you have the resistor, the ammeter, and the voltmeter all in series, and so when you go to add up the equivalent resistance, you have R plus 0 plus infinity because of the voltmeter, which basically means that the equivalent resistance is infinity for R2, which means there's not going to be any current flowing through this one. Okay, so which of the following circuits will not allow current to flow? That would be 2. All right, that's obviously bad as well. The issue with 3 is that the current is going to come out, it's going to hit this junction, and it has 2 options. Either it can go through this path, which has resistance R, or this second path. the resistance on the second path is going to be infinity plus 0, which is basically infinity, which basically means that no current is going to go through this outer path, which means that no current is going to make it through the ammeter. And so in this situation, the ammeter is going to read 0 because it's not actually measuring the current going through R. Okay, and so this circuit 3 would work, except that you're not actually measuring anything successfully because the ammeter is going to read 0 even though there are amperes going in the circuit. They never actually make it to the ammeter. Okay, so there you go. Oh, and the answer to the last question is 1. All right, so pause it there if you need to look at that some more. Okay, try to enter example 2 on your own. This is from an IB test a couple years ago. Okay, so an ideal ammeter, this is just something you just need to know, has 0 resistance and should be connected in series to the resistor. So the answer there is D. This was a super easy question as long as you know that basic fact. Okay, so sometimes you just need to know basic facts like this. All right, and take a look at example 3. I'm not going to explain this one, but I will give you the work after you after you answer example 3. So try to do example 3 on your own. Okay, what is the reading on the ammeter given the circuit? Okay, each component has a resistance of 2 ohms. So see if you can figure that out. Um, and notice that we are told that the ammeter has negligible resistance, which basically means it is an ideal ammeter. Okay, so see if you can figure that out. Okay, so hopefully after watching this video, you have a better understanding of the concept of series and parallel circuits, as well as measuring devices like ammeters and voltmeters. As always, please let me know if you have any questions, and I'll see you guys in the next video.